All right, let's talk about the invisible force that really runs our entire modern life, the processor. It's this silent, powerful brain inside pretty much everything we own, from our phones to our cars. And honestly, it might just be the greatest piece of technology humanity has ever come up with. Okay, let's get into it. And that, right there, is the central mystery we're going to unpack. How is it possible that something so incredibly small, seriously, often smaller than your fingernail, has enough power to create entire virtual worlds, connect billions of us, and even start to, well, to think? That's the big question. First off, you just have to appreciate how completely surrounded we are by these little silicon brains. They aren't just tucked away in our computers anymore. No, they're the tiny engines firing up our smartwatches, our TVs, our gaming consoles, even our refrigerators. They are the architects of the world we live in now. I mean, think about it for a second. That simple little swipe you do to look at photos, or that tap to send a message, or a click on a link. Every single one of those tiny actions is a command. It's an order that gets sent directly to a processor, which then makes the magic happen. So how does a piece of silicone actually think? Well, what's so wild is that all this incredible complexity is built on an idea that is absurdly simple. It all boils down to one single microscopic component that acts like the most basic switch you can possibly imagine. And that component is the transistor. That's it. It's just a teeny tiny electronic gate. It can either be open, which lets electricity flow through, or it can be closed, which stops it. On or off. That's the whole deal. It's like the atom of our digital universe, the single brick that everything else is built from. And here is where the genius comes in. That simple on or off state becomes a language. We just decide, okay, the on state means 1, and the off state means 0. And bam, just like that, you've got binary code. That's the native language for every single computer on the planet. Every photo, every song, every single letter in this sentence is, at its core, just a gigantic, massive string of these ones and zeros. Yeah, probably the best analogy is to just think of it like a water tap, but for electricity. You turn the tap on, current flows. That's a 1. You turn it off, the flow stops. That's 0. Simple, right? Okay, now imagine doing that billions of times every single second.
And no, that's not an exaggeration. When you hear about a processor's clock speed, like you see 3.2 gigahertz on a box, that number is literally telling you how many times it can flip those little switches on and off every second. So in this case, that's 3.2 billion times. The speed is it's staggering.
So obviously, one little on-off switch isn't very smart on its own. But what happens when you combine billions of them? Well, that's when you start to get a structure that can do math, make decisions. You get something that can essentially think. This is the anatomy of a digital mind. A modern CPU, the central processing unit, is kind of like a super organized office. You've got the cores, which are like the little mini brains doing the heavy lifting. Then there's the control unit, or CU, which is the traffic cop, directing instructions and telling everyone what to do. The ALU, the arithmetic logic unit, is the dedicated calculator that just crunches all the numbers. And the cache, that's like having sticky notes right on your desk, super fast memory for data you need to grab in an instant. And all these parts are locked in this constant 3-step dance. It's called the CPU cycle. First, the control unit will fetch an instruction from your computer's memory. Next, it has to decode that instruction to figure out what it's being asked to do. And finally, it sends that command off to the right part, like the ALU, to execute it. Fetch, decode, execute. That's the heartbeat of the processor, and it's beating billions of times a second. But here's the thing, a CPU can't do it all. It's a generalist. It's amazing at handling a few complex tasks one after another really, really fast. But for things like gaming or AI, you need a specialist, and that's the GPU, the graphics processing unit. Instead of a few super powerful cores, a GPU has thousands of smaller, simpler cores that are absolutely brilliant at doing the same simple task over and over and over again, all at the exact same time. That's what gives you those incredible graphics and what lets us train huge AI models. Okay, so we've got this incredible blueprint for a silicon brain, but how on earth do you actually build something that has billions of parts that are too small to even see? Well, this leads us to what is, and I am not exaggerating, the most complex and precise manufacturing process that humans have ever invented. So let's just get a sense of scale for a second. A really high-end chip today, say a top-of-the-line GPU, can have up to 200 billion transistors, not million, billion, all crammed onto a little slice of silicon that's smaller than a postage stamp.
And as you can imagine, building something that precise, it requires an unbelievable investment. A single modern factory where these chips are made, they call it a fab, can cost over $20 billion to build. That is more than it costs to build the world's most advanced aircraft carriers. It's insane.
And the conditions inside these places have to be beyond perfect. These fabs are thousands of times cleaner than a hospital operating room. And why? Because the transistors they're building are so ridiculously small that if a single speck of dust lands on the silicon wafer, it can short-circuit the whole thing and completely ruin an entire processor. For decades, this whole incredible journey has been driven by one powerful guiding principle. But the thing is, we're now starting to hit the physical limits of that principle. And that's forcing engineers to get really, really creative about what comes next. And that principle is called Moore's Law. For more than 50 years, it accurately predicted that engineers would figure out a way to shrink transistors down and basically double the number they could fit on a chip every 2 years. This reliable, exponential growth became the economic engine of the entire tech world. It's why our gadgets got faster and cheaper, year after year. The problem is, we're now trying to build switches that are only a few atoms wide, and the laws of physics are starting to push back. So, what's the next move? Well, the new era is all about clever design. Instead of just shrinking things, engineers are now stacking transistors on top of each other in 3D. They're designing chiplets, which are smaller, specialized chips that you can connect together, kind of like Lego bricks. We're also seeing a huge rise in dedicated AI accelerators, things like TPUs and NPUs, that are built specifically for the kind of math that powers artificial intelligence. And way out there on the horizon, we have the truly mind-bending potential of quantum processors. It really all comes back to this. A few simple on and off switches, arranged with a whole lot of human cleverness, gave us the entire digital world we live in today. But the journey is nowhere near over. As we start pushing towards chips that don't just have billions, but trillions of transistors, you just have to wonder, what new world are they going to unlock for us next?